Okay, I think if we are ready, we can start to have time to actually do everything. Yeah, so we are streaming all of the tutorials. So if you have any questions, we have the mic to say them on the mic to everyone who wants to join us on stream can hear us. Okay, yeah, let's start.
Okay. Well, hello. First of all, I'm super sorry. I thought it was 2:30, but we still managed to go through everything. I was planning that we would have at least 50 minutes to spare, so we can still make it. Right. So here today, I'm going to present an example in which maybe closer. Yeah. Okay. Good. So we are going to have a look at an example in which a very simple model can compete in accuracy with much more sophisticated models like a tuned XGBoost model or a tuned random forest. And it's not like a super trivial example, like some kind of linear regression or something. It is a data set that is quite famous on Kaggle, and it was used in a machine learning book. And it's about predicting medical cost, like the cost of a medical insurance based on the attributes of a patient that comes to, let's say, to you as maybe a bank or the insurance company, and you want to estimate how much this person is going to cost you. So let's see. First of all, maybe let's start with the basics. So the type of model that we are going to discuss, it's broadly classified as a linear model tree. Which, if you don't know what a linear model tree is, it's essentially a type of tree model. But the difference is that with a standard tree model, like a standardization tree, what you do is you partition the space. So you create subgroups, which in kind of more data science terms could be like groups of rows in your data set. So you find those groups in your data set with a tree structure. And in a standard tree, what you do is you feed a very simple model in each of the subgroups, which is simply the sample mean of the target variable in that subgroup. So if you want to predict, in this case, medical cost, you would create, I don't know, a few subgroups of people. And for each subgroup of people, you would predict for all of them the same constant medical cost based on the training data, would be the sample mean of the training medical cost for that subgroup. However, with a linear model tree, instead of fitting such a super simple model in the leaves, we do something a bit more sophisticated, not so much, but a tiny bit, which is fitting a linear model. We replace the constant by a linear model, and naturally now you can, the model is much more flexible, and you are not predicting the same exact medical costs for everybody in the subgroup, which is not realistic, as you can imagine, unless the subgroup is very small. And this brings me to the point of why would we care? What is the advantage of this type of model? Is the main advantage is that you can model rather sophisticated functions with a very small number of splits, very small number of subgroups or leaves in this context. And this is because in each subgroup, you're not just fitting a constant, you fit a whole linear model. But still, a linear model is a simple model. So still everything is very transparent, very simple. And the trees are very short, typically, with this type of model. So you trade away a little bit of, you increase a little bit the complexity of the leaves in exchange for reducing a lot the complexity of the tree structure itself. And typically the performance of this type of model is better or much better than a standard tree. You can fit almost any function with this type of model. Right. And for example, maybe we can compare this type of model with just a linear model. What is the relationship between the two? Well, a linear model tree is a more general case of a linear model because a linear model would be the special case of a linear model tree with zero splits, with just one subgroup, which would be the entire data set. If in that case you fit a linear model, then you could say that there is a depth zero linear model tree as well. So linear model trees include linear models. So therefore, it has a strictly more, let's say, flexibility than a linear model. You can model more things. And for example, non-linearities, you can model them natively. You don't need to do any feature engineering, as well as interactions. And compared to a standard decision tree, technically also linear model trees include standard decision trees, because as you know, when you fit a linear model, I mean, there are tests that you can run to detect if any of the variables has a statistically significant impact, or predictive impact, or explanatory impact. If it doesn't, then technically you could drop them and then still fit a constant which would coincide with the sample target, the sample mean of the target. So a linear model tree includes both the linear model, the class of linear models, and the class of standard decision trees. So it's a very, flexible and expressive class of models that still remains very transparent, very interpretable. So very nice, let's say, combination of performance and interpretability. And what is special about trust, which is the type of linear model tree that we are going to discuss today? Well, there are many things that are nice about trust. One of them is that it doesn't just fit a kind of run-of-the-mill standard linear model in the leaves. It fits some of the best type of linear models that exist today, which are relaxed or adaptive elastic net linear models. This means that this type of model, what it does, is a linear model, but it has some sophisticated regularization scheme that performs variable selection in some kind of optimal way, in some sense. So it selects for you the relevant features and drops all the others. And importantly, not just does this automatically and efficiently, but also with minimal bias. Typically, if you use lasso, for example, in order to drop, let's say, many of the features, the ones that survive will carry a lot of bias, because there is only one parameter that controls feature selection and has to deal also with regularization. So the only way to drop features with lasso is you crank up the penalty so that you kill some of the features, but that means that the features that survive have their coefficients squished due to the high penalty. With this type of relaxed or adaptive scheme, bias is minimized. So you achieve variable selection, usually quite aggressive variable selection, and at the same time, the bias that you obtain is minimal. So it's a very nice type of linear model. So that is one thing. Another nice thing about trust is that it does many things automatically for you, like encoding of categorical variables and also handling missing values. And it handles missing values in a nice way, which is that it can learn from missingness itself. What does it mean? It means that if a variable has missing values, trust checks if splitting on missingness helps or not. Just a very quick example. Let's suppose that you have data from some kind of survey. You ask people, I don't know, how much they make, and you also ask them how much they pay in taxes, let's say. And it could be that people that make a lot of money, they don't want to answer the question. Then you will see the pattern that if the person has the field of annual income missing, but then the person, for example, they did reply how much they make, how much they pay in taxes, you will see this consistent pattern that people that have this value missing of income at the same time tend to have a very high amount of taxes paid. So the response variable is very high whenever this variable is missing, the income variable is missing. Trust can also realize this and decide to split on missingness. So if the value of income is missing, then you go to the left. If not, you go to the right. And you fit a different linear model in each of the two subgroups. And then trust does more things that we will see later today. So maybe I can skip it for now. And here I mentioned M5 prime. M5 prime was one of the original linear model trees that was invented in the mid 90s, and in a study that I did, trust was better in terms of accuracy, but also simplicity. It used fewer splits and fewer factors were selected in each leaf. Right. So maybe let's move on, unless there's any question. We have had a look at what linear model trees are. Trust is a special example of linear model tree that has some nice properties. And if there are no questions, let's move to the actual kind of tutorial, more hands-on part of the tutorial. So here, what I did was I pip installed Trust Free. It should work in Colab, like all the dependencies and everything should be automatically handled for you. I'm going to run it again just to demonstrate. It might take about 40 seconds or so. So we can do it. You can do it in your time while we move forward. Then in the next cell, we just load the libraries that we will be using. As you can see, nothing super fancy. In the later stages of the tutorial, if we have time, we will briefly look at the performance of other models, and we will confirm that Trust does very well compared to XGBoost and other types of models. Right, so, okay, let's now load the dataset that we will be using. It is, I said, taken from Kaggle. It's a rather famous dataset, and let's have a quick look. It's rather small. It's more for like education purposes, I guess, but it will help us see. I mean, we will be able to highlight the main points that we want. And I must say, like in full honesty, that it's not always the case that Trust will be able to match XGBoost on any type of data set. That's not the case. It's not realistic to expect that. But I think it's worth trying, because in many cases, maybe more than you can, or maybe more than anyone could imagine, this situation will happen. That Trust is actually very competitive with very sophisticated and very powerful black box models like XGBoost, even after tuning. So let's quickly have a look at the data set that we have. As I said, it's a small data set, about 1,300 observations, 6 variables, 6 features, and very easy to understand. It's also a very clean data set. We will not have to deal with data cleaning or anything, which in practice, as you know, it's something that takes us most of the time, in fact. So we can skip that part here. The data set is very clean. So yeah, we have people is obese or not, how obese, let's say, or non-obese, number of children or dependents the person has, whether the person smokes or not, the region in the United States the person lives in, and the actual amount of medical cost that they pay to the insurance. So this is the variable that we want to predict, the charges, the very last column. So some quick exploratory data analysis tells us that there's a fair split between male and female. In terms of smoking, yeah, as you could imagine, maybe in the population, there are many more non-smokers than smokers, so like 80-20 split. If you look at the charges, so the medical costs for smokers and non-smokers, we see that, okay, I cannot show it very well, but we see that non-smokers tend to pay a lot less, like in medical bills, than smokers. And although the relationship is not super perfectly clean, it's quite obvious that smoking is a relevant factor just by looking at this. And then in terms of region, there's a fairly even split across all 4 regions in the US, so nothing relevant to discuss here. The distribution of the medical costs, as maybe we would expect, is highly right skewed. It's okay. I mean, this might make prediction a little bit harder in practice. Predicting these guys accurately typically will be hard, but other than that, it's okay. Our model doesn't make any super hard assumptions about the distribution of the target variable. If we look at BMI and insurance charges or medical costs, we see there seems to be, moderate association, positive association, although it's by no means super clean. Higher BMI more or less tends to be associated with higher medical costs, but as you can see, there's more to it than just BMI to predict medical costs. Something similar happens with age. There is some clear positive association between age and medical cost, but we seem to have kind of maybe 3 groups of people. Like people here, they have the same age, but quite different medical costs, so they must be different in other dimensions. Could be some of them are smokers, some of them are obese. So there seems to be at least 3 clear groups of people that age is a factor, but not the sole factor by any means, as we can see here, but it might be a factor. Right, so in terms of data preprocessing, as I mentioned, the data is very clean. There's nothing really we need to do besides encoding somehow the categorical variables. We will use the most common method, which is one-hot encoding. It's not the only one. Trust internally uses target encoding, which is nice in the sense that it preserves the dimensionality. It doesn't add more columns. With one-hot encoding, you will have, so if the variable has k classes, the categorical variable has k classes, you will have k minus 1 columns to represent that. So it can more or less quickly explode. In this case, it's fine. There are not so many categorical variables. So yeah, nothing much to be done in terms of preprocessing, which is nice. So we can run these. So, what we also need to do is to create the train test split, because otherwise it's not so interesting to show just the metrics in the training set. And let's see. So actually we are ready to go. As I said, we didn't have to do almost anything, just one-hot encoding and splitting between train and test, and we are ready to go. And this was actually, the one-hot encoding part was only done for the other models, because as I mentioned, Trust does everything internally. So you don't need to worry about anything. But for the other models, they cannot handle like strings. Like it doesn't know what to do with Southeast or things like that. So we are going to feed depth 1 tree. It means only one split, which means 2 leaves. And in each of the 2 leaves, there will be a separate linear model. This is sort of the beauty of this architecture, which is that you are free to feed a different linear model in each of the leaves. And potentially, I think it's not the case today, but in this example, but in many cases, the models in each leaf have nothing to do with each other because they are fit to different subgroups of the population. So this is the beauty that gives you a lot of flexibility and allows you to be competitive with very sophisticated black box models. So let's use a depth 1 tree, which will be enough. We can run this cell. And it gives you a little bit of information about number of samples, number of features, so on and so forth. Yeah, I must say, okay, I didn't talk about the parameters that you can use in Trust, mostly because the default parameters are quite sensible. One of the default parameters is the type of scaling that you want to use. Scaling, what I mean by that is that it is often good practice, and not only good practice, but necessary if you use regularization, to have your features in roughly the same scale, so that no feature sort of dominates by the sole reason that its units are, I don't know, millimeters instead of kilometers. So it has a very large numbers. So I was saying this because the default method is something called robust scaling, that essentially, instead of dividing by the standard deviation as in standard scaling, it divides by the interquartile range, which is a bit more robust measure of dispersion. Thing is that in some cases, like in this one, for the variable, I think smoker, 80% of the values are 0, and only 20% is 1. So the interquartile range would actually be 0. So it would not be defined. So the model automatically realized this and switched to standard scaling, which is very standard actually, to use this method. So yeah, just a little bit of kind of logging here. And yeah, and then we see that the test R squared of this model is 88.5%, which is very good. And we will see that none of the other models will reach this, although they will be close. A couple of them will be close. Okay, and here in this cell, if we run it, although you already see what it does, in this cell, we see, well, I was about to say we see the tree structure, but actually we see more than that. We see the entire model. So this is the entire model, not just the tree structure. Literally, the whole model is this. So you can write it in a small piece of paper, and that's the recipe to make any prediction. What does it mean? It means that when you, let's say you are evaluating a patient, let's say that you want to estimate the medical cost for this patient, you just first, well, ask or check the files to see the BMI of this person. If it's, let's say, roughly 30 or less, you go to the left. So you go to this subgroup. Otherwise, you go to this other subgroup. And a different model, different linear model will apply to this person depending on his BMI status. And one thing that is very important, which might not be obvious, is that this 30 actually has a meaning. So BMI of 30 is the threshold that was set by the WHO, the World Health Organization, to define what clinically obese means. And the model found it automatically. Like nobody told the model that maybe you should check what happens if the person is below or above the obesity threshold. It found this threshold automatically. So that's very nice. It has a very nice interpretation, which means, is the person clinically obese? Yes or no? If so, this model applies. Actually, the opposite. If the person is obese, meaning the BMI is larger than 30, this model applies. If the person is not clinically obese, this model applies. This model applies. Yeah. Okay. Sure. Yeah. I think the question was that if one of the subgroups, one of the leaves has a very small number of samples, if that could be a problem to fit the linear model. Yeah. So one thing that Trust does is it checks the number of samples, and it rejects partitions that result in a number of samples that is less or equal to p plus 1. P is the number of features. Why? Well, because if you have less samples than features, technically there are infinitely many solutions. That's not exactly true if you use regularization, but still the fit that you will get is almost arbitrary. And you don't want an artificially perfect fit just because you have sort of more degrees of freedom than constraints. So samples can be seen as constraints, columns or features can be seen as degrees of freedom. So you don't want to be in a situation in which you have so many degrees of freedom that the model that you find is almost kind of, I don't know, arbitrary. So what I opt to do is I reject those partitions. So you should never get a partition in which n is smaller than p plus 1. In this case, p plus 1 would be 7. So yes, going to your question, yes, it's not good if you have very small samples in one of the leaves. I mean, maybe ideally you would love to have more or less balanced seeds, but that's not always necessarily the case. But at least with trust, you have a minimal constraint that this allows super small seeds, leaves. And that's precisely because what you pointed, that it could be problematic. Yeah. So maybe very quickly, we see a couple of things. One is that H is a factor in both subgroups, so, and has a positive coefficient, meaning that older people are associated with a higher medical cost. And being a smoker also is a factor in both subgroups. However, there is a very interesting thing here. Maybe you have noticed, if you look at the coefficient of a smoker, what happens? 3 times. Yeah, more or less 3 times. So it means that if you are obese, smoking is 3 times as bad as if you are not obese. So there's an interaction between the smoking and obesity. And you can see it right here. You don't need any SHAP values or anything like that to see that if you combine being a smoker with being obese, this is very bad, according to the model. Yeah, in terms of expected medical costs. Now, if we run, so we have until 3:30, is that right? Yeah, I think so. Should be. Yeah. I think we're fine. Okay. So if you run this cell, this is one of the nice features, I think, which is that, okay, trust is natively interpretable, but still, imagine that you had, I don't know, 10 or more subgroups or leaves. Even if it's transparent, it is a bit hard to, I don't know, estimate visually or quickly by just looking at the model the relative importance of each factor. So it's nice if we have, some utility that we click a button and tells us in a rather reliable way, like what factors for the model as a whole matter most. And we have a few ways of seeing this information. And this is the importance method. And we want direct importance. We want to estimate the direct importance of each feature for the model as a whole, not in one particular leaf, but kind of globally. And we will see in a second why I say direct, because there's also the indirect importance or systemic, which is something more or less, I think, new. And we will see in a second. So what we see here very quickly, it's what we already knew, because we know the model almost by heart now. It's split at obesity, then age and smoker. That's it. So age, the higher the age, the higher the prediction of the model, everything else being equal. And this increases linear because we are using linear models in the leaf, so everything checks out. Gender doesn't matter. It's not used by the model. BMI matters simply as a kind of switch. If you are obese, then a different model applies compared to if you are not obese. So it more or less, the average effect of BMI is just shifting the average prediction. It acts as a switch. And region here, this is children. Children doesn't matter. I mean, has 0 direct importance. Yeah, okay, sorry. Okay, that, okay. Yeah, sure. Yeah, but I said children doesn't matter, not children don't matter. So I meant the children factor doesn't matter. Just for the record, since I'm being recorded. Okay, and the smoker, of course, matters a lot. The smoker status, and region doesn't matter. Doesn't have any direct impact. This is, confirming what we saw, and this is a bit hard. It would be hard to estimate this kind of just by looking at the model, which is the relative importance of each factor. Yeah, I mean, also by looking at this chart, it looks like being a smoker, it's a massive factor. And indeed, it is the most important factor for the model, whether you're a smoker or not. Then comes age, and then comes BMI. BMI is only used as a switch, but it's a rather important switch. It decides which of the two linear models will apply to you. And just a quick note, this relative importance is estimated with something very similar to, it's literally called permutation feature importance. And it does things a little bit differently compared to the standard implementation. For example, it's scikit-learn with the permutation importance method. The main thing that does differently is that it only uses one permutation, so it is very fast and very deterministic, or deterministic. There's only one permutation. The answer you get doesn't change if you click more than once. And the permutation is optimal in some sense that if you're interested, we can talk about this later. But essentially, it's permutation feature importance done in a slightly different way. Only uses one permutation. Okay, so I mentioned that we will look at the direct importance of the features. If I talk about direct, it means that there's probably indirect, or what I call systemic importance. What does it mean? It means that just because a feature is not physically present in your model doesn't mean it's not somehow still used by the model, or doesn't mean that the model doesn't rely at all on that feature, even if it's excluded from the model. As you can imagine, this could happen through proxy variables. So very quick example. Imagine that, I don't know, you have a model that wants to score people on their likelihood to repay a loan so that you decide whether to give them a loan or not. You're a bank or an insurance company. You don't want to use the raise variable because it might be forbidden. But you still use another variable that I think it's likely forbidden too, but let's suppose it's not forbidden. You use zip code. Well, yeah, the model technically doesn't rely on race, but it relies on zip code or district. And in New York City, if the person comes from Harlem or the Bronx, well, you can have a good guess about the race of the applicant. I think there's some correlation between residing in the Bronx or Harlem and your race. Therefore, technically, the model doesn't rely on race, but it's looking at your neighborhood. And maybe if it says Harlem, then it will rate your application differently. That's why I think it's important to have a way of detecting this indirect reliance of the model on some sensitive attributes. And that's why I developed this systemic variable importance method, which what it does very simply is it takes into account the correlation among features. And the correlation is not the only type of association that could exist between features, but it's a simple one. And kind of in my defense, I can say that I didn't use Pearson correlation, which assumes linearity, but Spearman correlation, which assumes only monotonicity. So it is not as bad as just relying on, plain Pearson correlation. And if you do that, if you take into account the correlation among your features, you see, for example, that region is in fact, used quite significantly by the model indirectly. Also a little bit children, and sex a little bit as well. We will come to that in a second. So the model doesn't use region directly, we saw that, but it still happens to have almost half the importance of BMI. So how is this possible? Well, it's because region is correlated with some other variables that the model uses. Which ones could it be? Well, let's have a quick look. So region is here. Oh, it's correlated with BMI and with the smoker. It means that there must be one region in the US that, I don't know, has a higher BMI than another. Therefore, if you know the BMI of a person, you could infer to some extent the region they come from. That's why region is indirectly used, and similar with the smoker. And if we have a quick look here, we run this, we see that the southeast region has a, I mean, not by a large margin, but substantially larger average BMI than the other regions. The southeast is like from Louisiana to West Virginia, and it sort of makes sense. I mean, you can imagine that in the south, you could imagine that the BMI could be a bit higher compared to other regions of the US. And similarly with smoking, there's another region. It's also the southeast. So the southeast also has a higher proportion of smokers. So if the person is, let's say, a smoker and obese, I mean, it's not guaranteed that it's from the southeast, but you know, it's more, if you had to bet on a region, you would bet on southeast. So there is some correlation between two very important variables for the model and region. So region, in fact, is indirectly used by the model. And lastly, we saw that sex is also indirectly used by the model. This is not good. Typically, sex is forbidden variable in many, let's say, credit scoring models. So you don't want your model to rely on sex, I would say, even indirectly. So, but the good thing is it's only 1% reliance. So probably should be fine. But still, maybe what we would like to do is not just to know that the model indirectly relies on sex, but would be nice to know in which direction it relies. So in which sense. Is your model going to predict a higher medical cost if you're a man or a woman? And well, the answer is well here in this chart. So this chart, what it does is it estimates the direction of the indirect importance, and we see that for all variables the direction is positive, meaning higher values correlate with higher predictions. And for sex, because it's a categorical variable, binary, higher means actually male, because the encoded value for male is higher than for women. So in this context, higher sex means being male. So being male is associated with higher expected medical costs. Why is that? Well, any guesses? That would be a good guess. But based on the kind of heat map, which has to do with the correlation among features, it might be that males tend to have a higher BMI than women. And because higher BMI is correlated with, on average, higher expected medical cost. Higher BMI, higher cost, but being male is higher BMI, so being male is higher cost, in a very kind of simplistic way. So that's why, even if sex is not used directly by the model, in a very indirect way, if you know the BMI of the person, you might have, if you had to bet, if the BMI is very high, if you had to bet, maybe you would bet is male. So you have a little bit of information by knowing the BMI of the person. Okay, so And now let's turn to, so far we have looked at what we can call global importance analysis. So we look at the model, and globally we had a look at what are the most important variables for the model as a whole, like globally. And we also had a look even at the indirect importance. But usually it's also very interesting to audit a particular prediction. So for example, imagine that, I don't know, that based on this information of our expected medical costs, we need to decide whether we make business with this person or not. Maybe if the expected medical cost is too high, we say, okay, we are not going to cover you, find another insurance or something. So the person might be like, okay, but why is my prediction so high? Like, can you give me an explanation? Otherwise, I'm going to sue you. Or maybe I'm going to sue you anyway, but I want to hear the explanation if you have one. So with this, with this type of model, actually, we could give a very nice explanation if we look at the actual model, because it's very transparent. There's nothing kind of to hide. But still, it would be very nice if we can just click a button and get a very comprehensive explanation that can be read in plain English by non-technical people. So let's do that. So this is the explain method. So we are going to examine the prediction for a 27-year-old woman that is a smoker and slightly obese. So BMI is a little bit higher than 30. Yeah, the prediction was very high, and the woman is upset and is wondering why. Well, we know why, mostly because he's a smoker. That is very bad. And also obese. Even if it's just slightly obese, for our model, it doesn't really matter. The person is obese, so the linear model for the obese people is the one that applies, which actually penalizes a lot if you're a smoker. So we actually already know more or less the answer, but let's run this automatic report that is very nice, especially for, you don't need to be like a specialist statistician to have a very good sense of why the model predicted such a big number. So, okay, so the prediction was $38.5 thousand. The actual number was about 35. So it was a bit off, like 10% off. It's not so bad. So yeah, bottom line, actually, the true medical cost for this person was quite high. Question?
Yes, I'm wondering, since you have this change of... Hello. Yes, thank you. So I'm wondering, since you have this change of model at like discrete value, is it possible that there's a higher error in that, like closer to the change? Like if you're really not very far from there, that there's really a lot of error.
Yeah, that's a good point. I think so, yeah.
It would be interesting to check that. I don't know if that's easy or not. But
it wouldn't. Okay, it wouldn't be super easy, but not so hard. You cannot do it easily with the trust model. There's nothing that you can force a split, but you could do it because it's a very simple model. You could do it kind of programmatically. So you could do kind of, if BMI is in this small interval around 30, I don't know, go left or go right. So apply this linear model or this other one, and you could check kind of how sensitive the final results are to slight deviations from the threshold. Yeah, it's a good question. I think so. Intuitively, there could be, yeah, it is a spot that could cause some problems, because you can imagine that a little bit of a difference shouldn't cause such a sharp difference. Yeah, that is, I guess, a weak point. But it's very hard not to have this kind of sharp discontinuities in a tree model like that. Question?
Maybe you could weight more the samples that are closer to the edge, and then make sure that you don't make so much error with those.
When you train the model, the edge changes, so you evaluate every possible splitting point, more or less. So you would need to change the weighting every time. But one thing that might actually help that is that even if there is a typically discontinuity, So imagine you're fitting like a parabola like this. So there might be a discontinuity here at the vertex, and you fit one line on each side. It's not guaranteed, and typically it won't be the case, but it's possible that the two models sort of almost, let's say, overlap, or they meet at the vertex almost exactly. So there could be a discontinuity, but typically the model will be almost smooth even at this point. So I think in theory, yes, it's a point that could be problematic, this threshold. But in practice, I think that the discontinuities are not so big. They are almost connected, I think, in most cases. So the overall model is not fully smooth, but close to smooth even in this point. Yeah, good question. So, okay, so let's have a look. So, okay, this report, it checks different things, and the first thing that it checks okay, if there is at least one split, it runs a SHAP analysis, because otherwise it's very hard to quantify the importance of the splitting variable, like in this case. If there would be no split, so it would just be a linear model, in fact, we wouldn't use SHAP. We would use an exact estimator, which, I mean, it would be just had to do with the beta coefficients of the linear model. But because we have one split at least, we use SHAP to estimate how the value of each feature contributed to the final prediction. And as we see here, being a smoker added almost $25,000 compared to the average person in our data set. So being a smoker is very bad, also for this reason. The medium BMI also, funny that they call it medium. This medium thing is calculated empirically, so it really is medium, but 31.4 is obese. So in this data set, the average person is obese, more or less. That's what it means. And yeah. But then being young, so having a low value of age, actually decreased the prediction with respect to the average case in our training sample. So yeah, the person is rather young, that's good, but smokes and is clinically obese, so that's bad. That's why the overall prediction is quite high. And this is the factor contribution to the prediction. It's the same data, but expressed in a pie chart. And of course, this is being a smoker accounts for most of the, this high prediction value. BMI a bit less, and age has a small impact. Then we check also the closest profile, and we see that there's somebody in our data that is more or less identical to this person, except for the age. And as we would expect, the model predicts a very similar value, more or less $1,000 less. And this is because this person is younger. So it gives us some confidence that someone that has a very similar profile is scored similarly by the model. So the model is smooth, at least in this case. And the next step in the report is that it explains more or less in non-technical words how exactly the prediction was made. And the prediction was made because the person falls in the group with BMI larger than 30. And there are two key factors in this group. And being a smoker, or actually not being a smoker, is associated with lower values of charges, which is the variable that we predict. And age, again, being younger, is also associated with lower values. So it is explaining that, okay, this person was rooted to this group, and in this group, these two factors are what drive the prediction exactly. Not as an approximation, but the exact reason. And it is explained in non-technical terms, so nothing to do with beta coefficients or blah, blah, blah. And lastly, it compares this person with the two most extreme cases seen in our data. One is the person with the lowest prediction and the person with the highest prediction. So we can see that, okay, it's like it can always get worse. So there's a person that was estimated some charges of 48,000, And it was because the person was still obese, but 64 years old and also a smoker. So I guess the main difference is the age. So it is a person that has all the risk factors that the person of interest in this case has, plus is almost 3 times as old. And being older is bad for this model. So that's why it can always get worse. So if you get older, then the model will estimate a higher expected cost. On the other hand, this person has a very low estimated medical cost because is a non-smoker, has a low BMI. I mean, not super low actually, but at least not obese, and is very young. So it kind of makes sense. Right. And then there's something else that we could do. We could also be interested in comparing this woman with someone else. And this idea came to mind when I was thinking about some other hypothetical applications of this type of analysis, which is like, imagine, I don't know. So you write an exam, and then you want to check your exam, and then you go to see the professor, and it's like, why do I have this score, very low score? Are you sure you didn't make a mistake? And then sometimes, I mean, I've seen, like last semester actually, there was a student that told me, but I know that my friend did almost the same as I did and got a much better score. And I was like, okay. I mean, I cannot, like, I'm not going to, compare the both exams, but it gave me the idea that it would be nice to at least kind of internally, maybe not tell the student, but internally run this check. Is it true that someone that is very similar had a very different prediction in this case? Or if you want to know, for example, another example, why this person was denied the loan and this other person was approved. What is the main reason? With this method, the compare method, we can do that. We can compare two specific instances and understand why the model has different predictions for each case. And it will give us, hopefully, peace of mind that the model is not discriminating against any particular person. So, for example, in this case, we compare this woman from the earlier example with a male that is about almost 10 years older, but has a lower BMI. What is the 0? I guess is the kids, and no, it must mean non-smoker, and lives in Europe. Let's say it could be even a different region. It doesn't need to be one of the values that we have seen in the data, which was restricted to the regions in the US. So what would happen with this hypothetical person? How would it compare with the original woman? Well, the first thing we do is we check the profile similarity. Well, I mean, we can see they are not very similar. So the sex is the opposite. The smoker status is the opposite. Age is kind of similar, but not so similar. Like there's a 10-year gap, more or less. But they are similar in terms of number of children. Both don't have any children. So the model using angular similarity, which is kind of conceptually similar to cosine similarity, which I think many of you are familiar with. Based on angular similarity, it determines that, the two profiles are not very similar. 50% means they are completely unrelated. Okay, 100% means they are identical. 0% means they are completely opposite. So a score of 50% doesn't, it might seem it's kind of close, but actually means they are completely unrelated. And in this case, it's less than 50%. It's 46%, meaning that they are very unrelated and actually a little bit opposite. And with this chart, maybe let's move this. With this chart, you can really see that they are mostly opposite profiles. And that's profile 2. And this is the woman because this is the smoker one. This is profile 1 and profile 2. Right. And now we come, so we have checked that they are on paper very different profiles. So it would make sense that their predictions are also quite different. So let's check that right now. We see that, okay, so one prediction is $38.5 thousand. That's the prediction for the woman. And for the man or the male, it's like 7.3. There's a difference of $31,000. There's a big difference, but that's because also they are very different profiles. And we can have a look at exactly what factors drive that difference. So not the factors that drive each prediction, but the difference in the prediction. So the main factor is the smoker status. That explains $27,000 out of 31,000 of the difference. Then BMI, a little bit, about $6,000. And age actually would bring down the discrepancy in that sense, because the woman is younger. So it would compensate for the other factors a little bit, but not by a lot, only $2,000. So yeah, the main culprit is being a smoker. That fact alone adds 27,000 compared to the other profile. And this is the feature contribution to the prediction of each profile. So for the woman, being a smoker drives a lot of the prediction. For the male, it's a bit more nuanced. Smoker being no, so non-smoker is also very important detail. Age actually decreases a little bit the prediction compared to the average age. I guess the average might be maybe 40 or something. And BMI also lowers a little bit the prediction compared to the average BMI, which, as we saw, the average BMI is more or less obese. So yeah. Okay, any questions so far? If not, let's quickly check the performance of other models on the same data set. I'm going to run these. It might be a bit tight. It's going to take about 5 minutes to run. It's doing like hyperparameter tuning for the XGBoost and the other models that we consider. But we know the results. They are here down below. We can leave it to work in the background. So here are the results. I don't know if you can see, but we see here that test R square of, let's say, for example, XGBoost is 88%, random forest is also 88. Lasso is rather low, 76%. Decision tree is actually surprisingly good in this case, but trust free is a little bit higher than the others. The difference with XGBoost and random forest is rather small, but nonetheless, it's nice to see that a very simple model, for example, random forest uses 250 trees. There are 4,000 leaves in that forest. This means that each prediction is the average of 4,000 predictions. Sorry, not 4,000, 250 predictions. But there are 4,000 different subgroups possible. So yeah, it is maybe a bit too flexible. Although this was the combination that was chosen as the best one by the, through cross-validation. And compared to the lasso is just a linear model. It's very simple. But technically, it uses more parameters than trust because it uses the full 6 features. It was unable to kill any of the features, even if you would imagine that it should be able to do so. Whereas trust kills 4 out of 6 features in each of the 2 leaves. So in the end, you could argue that this very simple tree is in fact simpler than a linear model, which is quite crazy. And in this case, the performance is very good. It is about the same as a tuned XGBoost. So as I said at the beginning, this will not always be the case, but I would say it happens quite often that at least gives a competitive performance. So I think it's worth trying. And I would say that's it. My takeaways would be that with a simple model like this, you also gain kind of for free very nice insights, like the obesity status of a person matters a lot. And actually, the split was found at exactly the obesity threshold that was kind of set officially, let's say. And this was not, told the model in advance. And we see also very nice things like if the interaction between obesity and smoking, that this type of insight will be very hard to obtain with black box model. And we get it for free with this model that at the same time doesn't sacrifice predictive power in this example and in many others too. Okay, so thank you. If there are questions, I will be happy to answer. Thank you. Mm-hmm. Okay.
I can speak loud.
We need to turn it on. Sorry.
One, two, three.
Mm.
Right. Is there a similarity here between the rule fit? Because I remember a long time ago I used the rule fit. Mm-hmm. Are you familiar with that method? And is there some similarity here?
Yes. Yeah, I'm familiar. So rule fit, it first fits like an ensemble of trees and then extracts rules, and then selects the rules with L1 penalty, something like that. So in the end, the model is a collection of curated rules extracted from a tree. So the rules could be the person is obese and smoker, for example, things like that. In my experience, this is I believe I included, or maybe not in the paper that this algorithm implements, but in my PhD research, I did include rule fit. The performance is similar. It's just that the number of rules that it uses is usually very high, like in the hundreds. And this one is a simpler model. The performance is similar. It is quite good. It performs well. Well, yeah, this one, because the other one, I mean, if you want to interpret the whole model as a whole, you would need to interpret the 200 rules. For a particular instance, you would just kind of interpret a few of the rules, like if the person is obese or not, if the person is a smoker or not, if the person blah. So for a particular instance, the explanation might not be very hard. But if you want to understand what the whole model is doing, you would need to somehow interpret all the rules simultaneously, and it's impossible. Mm-hmm. Yep.
For this particular use case, it seems all nice and good. I mean, you get a very sparse tree, less depth. But what if for another use case, the resulting model is perceived to be an underfitted model? Would there be like any tweaks to increase the number of depth or?
I mean, yeah, the tweaks would be to increase the depth of the tree if you have enough data. You can try that. So here we specified a depth of 1, but if you don't specify anything, it's going to check from depth 0 to depth 4. By cross-validation, we'll choose the optimal depth. You could go past depth 4, although my experience is almost never worth it. Yeah. Depth 4 means up to 16 subgroups. So yeah, the answer would be that you would need to increase the complexity of the model if you have enough data.
Yeah, but I tried to remove that parameter in the start and still I got like depth 2.
Yeah, well, because it was the optimal. Okay, so it chooses the optimal level of complexity for your data.
Through cross-validation. Okay.
Yeah, exactly. Yeah. Yes.
Thank you.
Mm-hmm. Any other questions? Yes. Yeah, I have. The only thing is that if you have a very small data set, then and you have a lot of features, the model will refuse to split for the reason that I mentioned before, because it doesn't want to have a subgroup with less samples than features. But as long as you have more features than samples, it will try to find groups. And maybe it will decide that the best thing to do is to find just the whole group as a one group, or it could decide to find a few subgroups. So yes, the short answer is yes, I tried with a small data set, even as small as like 60 samples. But then the number of features, it was maybe like 5 or something like that. With 60 samples, actually I tried one example that it was like 70 samples and 4,000 features. So it was like a genomics data set. In that case, what it does is it just feeds a linear model, doesn't split. And it still feeds a linear model that does automatic variable selection and with minimal bias. So it's still, in that case, if it cannot split, it would still provide a very good linear model, typically better than just a plain linear model that doesn't do all these things. So yeah, it should work also with small data. Yeah. Thank you. Thank you so much.
You managed to be perfectly on time.
Okay, great.
Thank you for the talk. Thank you. Yeah, thank you for the next time. Yeah. Okay. Grab your. Thank you.
Hello, hello, hello. All right. Can everyone hear me fine? Excellent, excellent. Huh? I'm already here. I'll beat you to it. So, is it being recorded?
I think it's not our task, so
Okay.
when there will be a problem, someone will come and.
Let me see if I can. Okay, we are recording. All right. Sorry for the delay, everyone. I was setting up a few things over there, but welcome. Very glad to be here. I'm very glad that all of you can join me today in this session. So, this session was meant to be a talk, and Martin asked me if I could do it as a tutorial, and I agree. So, it's going to be a talktorial or a slideshow, if you may, because it has a big part where I am explaining different things and I am kind of like taking you through a history of how I got to the use case that we're going to be talking about today. And then I'm going to show you the different ways in which you can fine tune. Fine tuning models is sort of in comparison. I don't like to use the word easy in any kind of situation, especially technical, because nothing is easy within the certain amount of perspective. So technically speaking, if you have built an LLM, if you have built several and fine-tuned several, then it is going to come easy to you. If you have never done it, it is not going to come easy to you, no matter how much I say that word. So I'm going to try to keep it outside of my vernacular. And I'm going to show you the things that I have done with fine tuning. I have worked with text, with audio, with images, and most recently this year with video. Two of those four, to some degree or to a large degree, can only be done in much larger computers than mine. So when we get to that section where we talk about those two modalities, in particular images and video, we're going to jump into different places where I'm going to show you how you can accomplish it from there. And then I'm also going to show you the code. I have put here the link to all of the materials about the workshop. Initially, what I wanted to do, because of this, because of the constraint of the resources, was to use the Wi-Fi over here and then walk you through fine-tuning, where all of us will be in a whiteboard. That whiteboard is in there, but the Wi-Fi is actually, the network will not allow me to hop from one device to another without a specific setting that I didn't ask for in advance until today when I was testing it. So it is available. There's two commands to start it up, one to install it, and then another one to start it up. So you can follow along with me. If you have an OpenAI key as well, you can do a bunch of the stuff that we can do. And then I'm going to walk you through some of the things that you can do as well with it. So there is a whiteboard, there is this deck, there is a Jupyter notebook, and there is an application. And all of them are sort of to play chess and also to fine tune. So, all right, so let's get started. So when I first found out about chess, that's my face over there. I was like, what is this thing? I need it. I need to know what it is. I need to play it. And then, so I ended up coming across this famous book that I don't remember what it looked like. I don't remember what it had in it. But if I would have remembered the words in it, they would have probably read like this, completely incomprehensible, at least to me at that age. Truly this force and all doubles reluctant that reading final small book of thou, whatever. You get the point. I couldn't understand it. So it wasn't too long after I got that book, and it was at a local bookshop. I am from the Dominican Republic, by the way. So that's what I ended up finding. Also, it was in Spanish, not in English. And then April, fast forward from that long ago, I'm not going to tell you how long it was, because then you'll be able to age me. So fast forward several years later, not too many, I came across Duolingo. And I have been using Duolingo officially today for about 10 years, I believe. And it wasn't until I was in Japan in around March and April that I went into the app to select a new language. And when I selected a new language, I saw, oh, shoot, they have chess. Let me actually look what this is about. And it just so happens that they had come out with it. If you see the date for that blog post, they had come out with it on June 10th, 2025. So I'm quite late to the party, if you think about it. And then I started playing. And honestly, I just fell in love with it. The user experience, the touch, the haptics on your phone whenever you use it, and it starts kind of like, and also the sarcasm of this little fellow over here whose name is Oscar. So yeah, his mustache will not be denied. So it went on from one game in the first day when I came back to 5 games, to 20 games, to 500 games. So yeah, so it was 5 games a day, 20 games a day, and then 500 games in the first month alone. Until at one point I realized, fuck, I need to watch the Queen's Gambit. I haven't. I don't even know where this thing is at. Let's go through it. And then as I went through it, I was like, okay, well, let's improve a little bit. If you have seen, if you don't know what this thing is, I don't even think the people that created it know what it is, but it stands for how good you are. And that right there just makes me extremely good at being average. So, which is all right. I'm okay with it. After a while, beyond the first month, bear in mind that this is just 3 months ago, I'm already at 500 matches won. And keep this in mind. because this is extremely important for when we get to a point where if we are playing against AI, how do we calculate the cost of a token when it comes back to us? The thing that we get back when we send an API call to receive intelligence back to us, unless we are using the subsidized versions where we connect to Cloud Code for $20 a month and everybody's happy with it. Okay, so but then I hit a problem. Especially on the way back from in between my 500 matches and the trip to Japan, on my way back to Sydney, Australia, which is where I live, I hit a snag, and I realized, like, shit, I am addicted. I'm having withdrawal symptoms, and I couldn't play. And I was like, what is happening? I need this thing. And Jetstar, the airline that I was using, you probably know Jetstar, they didn't have anything. They didn't have any internet. And so then I said, screw this. And actually, because I was in a flight, it was more like this, because technically speaking, there was no table for me to flip. So I had one of these ones. And then, so a reasonable response to this, I'm like, I got accepted to EuroSciPy. I have a talk, but they asked me to do a tutorial instead. So I thought, what if I completely change what I had planned for my talk with less than a month to go? What could possibly go wrong? And then so yeah, so now we're here, and I have way too much content than I could possibly go in 90 minutes, which is great for you if you find this talk interesting and this topic interesting, which I hope you do. I hope that's the reason why you're here. And then, so then we're going to walk through a couple of things that I hope you walk away with it today, and also hopefully a little model as well. If you have something in your device, I hope that you can take the recipe that is in this repo to fine-tune your own model. So this was taken a little bit ago. This is the little application that I created. I have it on, I have an iPhone, but I also have an Android phone. And then the nice thing, the main reason why I got the Android phone is because I wanted to experiment with local models. I had never switched from Apple, and now I'm hooked to the Android device. I'm like, this thing is just incredible. So I'm talking to Gemma, I'm talking to any kind of model that I can. And the nice thing about it is that if you dig deeper than the surface layer, which is Python, on what you have, you don't even need to go low level. But if you dig a little bit deeper, you can go and see how kernels are created. A kernel, a GPU kernel, is something that allows you to run a model more efficiently in a particular device. That's why sometimes you see that when a new model architecture comes out, you don't see your favorite package or your favorite provider being able to offer it immediately. They need to wait until the code has been implemented for this new architecture to be able to run that and offer it to you as a service, as you are the user. So if I don't have a specific model that I have been experimenting with or available for the specific architecture of my phone, which is a Snapdragon 8 made by Qualcomm in the US, then can I code it myself? So that's why I got that phone. And then I started using models locally. And the latest thing that I did is that I fine-tuned a little Gemma model. And then I made a little TUI that is, by the way, available in the repo. I don't think I need the internet, but I'm just going to do it just in case. It is possible that I might need it. So I have the little TUIs called Chess TUI. It's not very elegant. It's not very it's not very sophisticated, but it does what it needs to do. And what I want you to pay attention to is like the way I'm playing right now, because these are the tokens. These are the things that an LLM is going to need to see or understand to be able to move a piece on the board. So you have on the row, you have A, B, C, D, E, F, G, H, and then on the y-axis, you have the numbers from 1 through 8. So this is going to be what you pay for whenever you fine-tune a model for whenever you fine-tune a model to play chess. And then here you can see that Gemma is playing against me and is moving the pawns in my direction. And as you can see, like I'm there, and it says it's developing the queen side with a slightly awkward pawn push and so on. But it doesn't really matter. What I wanted to show you here is after this, after I move this one, is where Gemma is running and how Gemma is running, because you can also do this yourself. So if you see here on the side, you're going to see 2 tabs. And then in the first tab, you're going to see, or sorry, in the second tab, you're going to see that I have the model running with something called Llama CPP. Have anyone here heard of Llama CPP before? Okay, I have 3 people. So for those of you that have not heard of Llama CPP yet, it is an engine to run models on device. You can technically run them in a server, you can run them anywhere, but it would allow you to run at a very, very efficiently models that have already been quantized. What does it mean to be quantized? Quantized means that if a model is composed of numbers and those numbers form the intelligence of the model. Think about it like every little neuron in that model's brain is composed of a very long number of 16 floating points, 16 decimal places. If you quantize a model, and this is a hand-wavy explanation, you kind of like take half of it, and now you have 8-bit precision, or eight decimals instead of not 8-bit precision, 8 decimals. And then if you take it even smaller than that, then you take 4 precisions, quantization level 4. So kind of like that's a hand-wavy explanation of it. So I have some resources for you to find out a lot more about quantization, and then we're also going to look into it here in a little bit. But I have a quantized version of Gemma run via Llama CPP, running on my device, that I can chat with it and just talk to it all the time. So my goal is to run it on my phone, record the wins, losses, and draws, keep the moves, and then replay the game. And the reason why I want to replay the game is because I want to get better. I want to become better than the average. But ideally, I would prefer to do this with a slight variation. If I simply train or fine-tune a model to play chess against me, one of the drawbacks is that perhaps some of the better models can do it, but it doesn't run on my device, and perhaps I'm leaving a lot of value on the table. So if I select something else, something very specific in which I want to get better, why don't I add it to the mix as well? And I'm going to show you how when we look at how do we format the data before we start fine-tuning. Data is the most important thing that you need to be able to fine-tune something. And so I would prefer, my personal preference is that I would prefer to win while taking as few opposing pieces as possible. And also just because Sun Tzu says it in the Art of War, he said the supreme art of war is to subdue the enemy without fighting. So that's kind of what I wanted to do. So we're going to talk about 4 adaptations, and we're going to focus mainly on the text one because you can do it in relatively smaller devices. Most image models, regardless of how much they are quantized and so on, they tend to be quite large, 8 gigabytes, 9 gigabytes, and it just goes beyond what any regular laptop can do. Same with videos. And if we fine tune one of those, even of 8 gigabytes, I do have a GPU in my machine, then we're just going to go and have coffee and then come back and hope that we can see some progress. So we're going to talk about text, image, audio, and video. So text can do more than choosing a move. And so what do I mean by that? So say, for example, have anyone here, I should have asked this question at the very beginning. Have anyone here played chess before? Okay. So you haven't at the back, and you have never played chess before as well? Not really? Can remember? Okay, thank God I put the rules in here somewhere. It's in the upcoming slide, so I'm gonna explain the rules. But every player has 16 pieces. You have 8 pawns, and then different kind of and those pawns can only move forward. And then the pieces at the back, they can move in very specific ways. Whenever a pawn makes it across the valley and all the way to the opponent's place, then you get to claim a new piece. And usually everybody goes for the queen, because why wouldn't you go for the queen? But you can get any other pieces at the back except for the king, of course. The goal of the game is that you want to check the king in a way in which he cannot move. And when the king cannot move and is cornered from different places with a piece of yours, then you checkmate the opponent. And chess has been in circulation for thousands of years now. And some people have even described chess as the pinnacle of strategizing and intelligence, and it can be related to life. And there's a bunch of books that talk about life, that talk about this, that talk about that in relation to chess. And I thought, like, what? Why the hell no? Let's actually relate it to something. Let's relate it to life. Okay. While the hand-drawn board illustration shows a generic tactical checkmate rather than Kasparov's 1997, Garry Kasparov was one of the world grandmaster for many, many years. He's a Russian player. Nowadays, he is more dedicated to philanthropy, and he's not in the top 10 anymore, but very, very great player. The first one to be beaten by AI. So there's an AI mentioned there. So Kasparov in 1997 played against Deep Blue. The position illustrated a trap modern software teams fall into daily. The white queen sitting on E7 looks like a decisive, impressive move, much like an AI-generated pull request that compiles on its first run. Developers routinely accept thousands of lines of unverified AI slop just to hit short-term output metrics, confusing sheer volumes with sound architecture. The chaotic pile of capture pawns cluttering the board's margin is the visual equivalent of a repository accumulating redundant functions, useless abstractions, and hallucinated dependencies. So I'll leave it up to there. It's actually quite hilarious, all the stuff that I was able to come up with, but I thought, why not? So we need the game moves. First thing that we need for our use case on text alone, we need a specific kind of way of winning, which is with as few moves as possible, or without taking that many pieces of our opponent. And three, can we also have a model that relates to scenarios of a game or the game log to a real world case use case? So those are kind of like the three things that we would like to do. But if we do come up with a model that can do all of these things, couldn't we also, I don't know, make a nicer, slightly nicer user interface than the chess TUI that I showed you a little bit ago? So Llama CPP, when you run it on your phone, you can access a local host with 1917 or whatever you put in it. I think it has a different kind of default thing, and then you can just open it in a browser and use it offline and talk to whatever model you loaded. So here I have the same Gemma 4 E2B, and I ask it, do you know anything about EuroSciPy, the EuroSciPy conference? Short answer, prefer. I do not have any specific real-time information about EuroSciPy conference in my knowledge base. However, EuroSciPy is a well-known annual international conference focused on Python and scientific computer. I think you nailed it. The TUI could just be one of the clients. And by the way, I didn't say this, and I should have. A TUI is a terminal user interface, something that you can run in a terminal that talks to your device resources, hardware. And if we want to know the client, something else that talks to the model, can we also put it somewhere else? If we're going to do so, then we talked about text already. What could we use to create something nicer? Well, we could use an image model. And not only could we use an image model, but perhaps if we have more use cases for that image model, we could also turn it into a type of style that we use more regularly. Think about it, if we have a base model, and then that base model, I gave all these three models the exact same prompt. Chessboard, from the perspective of a user interface, this design would be what a user sees when they go into the web app to play. So then that would be the first one. It kind of like looks mechanical. It kind of like looks cool, quite nerdy, to be honest. The second one is a little bit more right up my alley, hand-drawn. I love that design. And then you go, you touch, you move over here. It kind of like shows you where you need to go. And I kind of like that. But if you have a model that already has, like, if my style, I love hand-drawn stuff, things that look like kind of like rough sketches. Can I already have a model that has been adapted to, for any kind of prompt, give me any image that I request in the style that I want them, so that I don't have to type every single time black and white, hand-drawn style, rough sketches, and so on, which is not a big deal. But if you have more examples of what you like, you can make the model even better, and you can adapt it to many different scenarios. And then the last one, another style. If you want something a little bit more trendy, I don't know, and you want vehicles as opposed to chess pieces, then you can also do something like that. And I'm trying just to give you an example. I'm not trying to tell you that an image generation model is a UI generation model. It is not. I'm trying to tell you how you can change styles depending on how you decide to fine tune. And I'm trying to relate the use case that I pick because I pick chess. And then how can I as well make something or think of something, ideate of something better for the user interface of my application. Now, what about sound? Chess apps already have ship with sound, and they are very, very cool. So behold the beautiful Luna. Let me see if you can hear this. I think you should be able to hear.
My mustache will not be denied. With regrets. Focus, Oscar.
So when you hear those little sounds, if we are going to make a little application that we can open on the browser, can we also have a model that makes sounds? And I'm going to show you a couple that we can use for it. And I'm also going to show you an example that you can go and download and literally, hopefully you like it actually. But yeah, so we can create sounds for our chess pieces whenever they move and whenever they take on an opponent. So what would those sounds look like? So I generated these ones with different models. One of them is fine-tuned. So if we have, for example, what would the capture sound be? That one sounds awful. Maybe we can fine-tune it. Maybe we can make something a little bit nicer. Maybe we can play with the prompt and make something even better, because that one wasn't that great. What about if we have some background sound? Like in chess, sometimes you might want a little bit of silence to concentrate, like and calculate how many moves the other person has or the other player has. How many moves can you make before you are checkmate, or before you checkmate the opponent? So can you put a little bit of background song? So I'm Dominican, so I put bachata here. If you haven't heard of it, it's a genre from my home country, bachata. There's also merengue, and then salsa next door in Puerto Rico and Cuba. I can tell you right now that tried to be bachata. It did a very good attempt. And also, what if you are, I don't know, cooking, or you are walking around and you literally just want to have a game of chess? Can we also have a Gemma connected to a speech-to-text model, text-to-speech model that can tell us what has happened?
I can't believe that was the play. Bishop to f7-2. Take the knight and check.
So that would be really cool. Can we create a text-to-speech model? Can we fine-tune it to a voice of someone that we like? I mean, if it was Morgan Freeman, I'd be like, yes, I got to sell this. I got to make a product out of this. And then lastly, for the last use case of today, so you remember about 4 slides ago, we had a type of writing that was based on the game log, on the log of a game, how the pieces move and so on. So can we come up, so you can see here, like, while the hand-drawn board illustration shows a generic then Kasparov's in 1997, can we also adapt that and have another model that create prompts for us to pass it on to a video model that comes up with a use case? So remember that it was software engineers writing slop. So
Tests are green, let's push to prod.
Wait, what is this boilerplate doing?
It's awful, but it's absolutely awful. But I thought it would be funny, regardless, just to see something like this. That something like this is possible. So I don't know if you want to burn the world's energy on that kind of further slope, but just made into video. So what I wanted to get to by showing you these examples before we get into the code is one chess game or one chess game can become, or one model can become a move engine, a storyteller, a board designer, a DJ, and a movie director. But no single model can do all of that today, and no provider ships every capability at once. When you need one of them in your style over and over and over, adapting a small model is what makes it reliable, or might make it. It will save you a lot of time. It might save you a lot of cost, and it will make it more reliable to get what you need. So there's only one model that I am aware of today that makes all three modalities, and I think it is the latest Gemini Omni, that it can take in audio, images, videos, and text, and then it can output back the exact same 4 modalities. So if that is not the case, that there's not a single model that can do all of those things reliably, and if we do not need all of those things all the time from the exact single model, how can we make our own? Okay, so now that we saw some examples, why do we adapt anything? I just want to give you a couple of pointers as well, because I told you what you can do with fine tuning. I show you what the use case was, and then here I have why would you do it as well. Remember the amount of game chess that I have played? And if I play that at an API cost against a very decent model, one of the recently released models by OpenAI, GPT 5.6 Luna, it will cost about 58 cents, 400 inputs, 30 output tokens each. So let's say that 400 input is about, let's call it, maybe 50 games, maybe less than that. Let's say it's about 20 games, because even in a single game, you can have a lot of them. So if we have that, and that is about 200 times this, then we already have about $116. And also I'm thinking here in the price that they quote, which is US dollars. So we will have quite a decent amount, and I can get to you saw already, I can get to 1,000 matches in a month very, very easily. So I will pay quite a lot just to have my own engine that I can play against and can do more things for me than the regular ones do. So if you have a local one, then you can run it at 0 cost, and that's kind of one of the biggest rationales. For images, images is a little bit trickier, because it doesn't matter how, like the most useful models in image generation, they tend to be quite large. So if you have a fine-tuned version and is slightly smaller than the full one, the one that has the 16 precision, then you can spend much less, like orders of magnitude less. And especially when we get to that point where I'm going to explain what quanta is, like what the different methods do, then you'll be able to see, or at least build an understanding and an intuition as to how this works. So the difference when you rent a NVIDIA 4090 is about per generation, 10 seconds generation, about 19 cents. And then Flux 2, which you can find in Fold.ai, it is by Black Forest Labs. It is about 100 images, is about $2.10. It is quite cheap. It is really nice. For the audio, in 11 Labs Music, if you want to make some music, then you can get it like 25 minutes at about 15 seconds per minute. Then you get $3.75. You can generate a lot locally with audio models. The song that I played earlier was locally, and I have a couple of videos online as well showing you how to fine-tune audio models as well for what you need. It is trickier than it seems, because models don't understand audio itself. They understand images of audio, which becomes a spectrogram. And I'll show it to you in a second. Videos are very expensive, very, very expensive. especially per minute. And then videos can have different kinds of modality. You can pass in frames. You can have a starting frame of a picture that you want to start with. One of the use cases that, for example, at work, we have tried, and especially early in the year, where you have a user comes in and they want a template, say a Christmas template or something like that. They're with their family, and then we generate a nice background around that picture of them and their family, and then we have that as the initial frame. The last frame, instead of them sitting down, they're kind of like standing and then walking towards a Christmas tree with Santa Claus. So then you have now the initial frame and the ending frame, and now you want to interpolate between those two and have them have actions. If their whole body is not very visible, like they cannot see it, then the model is going to make up what they look like and how tall they are, and so on. So there's so many tricky things to get right. You can go text to video, you can go image to video, you can go keyframes to video. So you can also have many more keyframes, and then just have the model fill in the gaps for you. That tends to work out quite well. And you can also have style transfer of video. So all of those have a different kind of cost, and this adds up so much. And I have not seen anything that can run on device and has a good output yet. There are providers. The key thing of all of this with cost and relation to where you use them and how is that at the end of the day, a provider does not have access to your data or to your company's data. They might have access to scrape data, licensed data, public data, and synthetic data. There's a really nice paper from Hugging Face or kind of like a white paper, and it's called the Synthetic Data Playbook, Generating Trillions of the Finest Tokens. It is a really good read if you're interested in AI and how what it consumes. So I highly recommend you check it out. And by the way, if you have any questions at any point, I should have said this since the beginning, but please just stop me and ask away. Then there's also the private license review or newly created examples that define the task that you are interested in. In my case, playing chess or generating cool designs for the chess UI. So hosted fine-tuning still sends the data to a provider. But if you have the data locally and you have access to a GPU, then you can do it yourself in some cases. Okay, so providers do not know your style. I had a little bit of fun with this one, but since this just happened recently, well, Spain, Spain did really, really good. I hope they enjoy it. And then there's the Argentinian emo fellows. So if that's a kind of style that people like, or kind of like not emo, but just a different kind of style to use. Then there's also a style transfer. So does anyone here work at a corporation? At a big company? More than 200 people, 500 people? Okay, we have one. So you are is it safe to say that you are very used to corporate speak? Yes. Okay, good. So this was the latest. There's a company that was founded by the former CTO of OpenAI, Mira Murati, and they're called Thinking Machines. And recently they released a demo that I just thought it was absolutely fabulous. And how they have all of their models are very easily fine-tuned. This is their value proposition, and they're also making foundation models. And then in this recent one, they fine-tune a voice model to translate not from English to another language, but from berating someone to corporate speak. And it's absolutely hilarious. So let me play it to you.
You're going to translate what I say into HR speech, okay?
Exactly. I'll be reframing everything you say into uplifting professional language instantly.
Hi, Alex. I cannot stand your lateness.
Hi, Alex. We'd love to explore opportunities to enhance your timeliness and morning engagement.
You cannot expect the rest of us to rearrange our workflow.
Let's collaborate on a schedule that ensures everyone stays aligned and included in those key morning sessions.
I don't care if you need to sleep at your desk.
Let's champion a culture of vibrant morning energy, where your refreshed presence inspires the whole team to shine brightly by 9 a.m.
It's absolutely hilarious. I love that. Like, just for that alone, they should have a lot. Right. Even if you don't work at a big corporation, I'm sure people here have, some of you have experienced corporate speak, and I mean, it works. It does something. The other thing that you can do as well is that maybe if you really like or love corporate speak, you can also have it in your images and your designs. And you can have something like this: mission critical, win, disrupt, get disrupted. You can send that to someone in Etsy and they'll make that that exact same design for you. So you can get really creative with how you fine tune things to your liking. And what I wanted to bring across with that is that a provider will never know your style. Only you know your style. And that's the beauty of taking all of these models. And if you have enough data to turn it into something that only belongs to you or only works for your use case, it's just magical. It really works incredibly well. So to bring this section kind of like to a wrap on what you can do with fine tuning versus why would you do it, because a provider doesn't have your data, doesn't know your style, and also the cost involved with something that perhaps is not necessary for you to have, if you can have something cheaper and faster. So in this world, there's data we think exists. There is data that we can access. There is data that we can legally use inside of that. And then there's also data relevant to the task that we have. Then there's also private or newly created data that we don't know exists, that gets generated every day. If you take the slope out, then that circle might be a little bit smaller. Who knows? It might be a little bit bigger because there's also unknown unknowns. And then in the middle, you kind of like have the stuff that you can train a model with and the stuff that you cannot. If your data lives in the use case of held out data that nobody owns, then you are in a good position to make something more bespoke to yourself. Cool, bro. So now what? Okay, so this talk workshop-ish is about fine tuning, but don't reach for it if you don't need it. You can prompt very well until you get what you need. You can create a spreadsheet with the prompt and the output, and then just say like, this was really good, this was really bad, this sucked, I didn't like it. You can also have tools, rules, and exact calculations. You can provide, today, most providers give you an option called skills. Those skills are kind of like a way for you to do something that you can provide to a model. And then you can check how many times he gets it right, how many times he gets it wrong. And then you can generate your own little data set from interactions that you do or have with much bigger models. You can also have them, give them the ability to retrieve data depending on the provider that you're using. That's already available to you. But whenever you have a fine-tuned version or something else, something perhaps smaller or cheaper, and then at the very end, you can fine tune. So the chess app already combines nicely something called a library called Python Chess, and it owns the legality of a move. I'm going to explain what that is here in just a second. So use the hosted model when it is the better tool. Own an adapted model when the repeated task, the data, latency, or the offline requirements just justify. Okay, let's do it. So I mentioned I was going to explain briefly. I added a slide here explaining the rules of the game. So white always moves first, then black moves. Every piece has a fixed move set. The ones at the front, they can only move one at a time, and they can sort of take over a piece diagonally. There's also a weird move that you don't need, that you don't hear or see very often, and it's called en passant, French, very French. And it is when a pawn comes right next to you, you can kind of diagonally, without it being above you, and diagonally kind of like beat that piece. But sorry. So imagine you have one of these ones comes right here, right? And then it moves from here to here. Then this one can move there. But more often than not, you cannot do that. You can only beat it if it's there or there. But if it moves from there and I didn't notice it and it moves here, then I can go to that one there immediately. And it's called en passant. It's kind of like I beat that piece in passing. And it is a legal move. So check and checkmates, you attack the king. If then there's a check. If there is no legal escape, the king. So, okay, one more thing that I should say. Rooks, they can move diagonally to the left and to the right. the horse here or the knight, it can move in an L. So 1, 2, 3. So 1 to the side or 1 to the side. It can move in any direction, but in an L. This one's here, the bishops, they can move diagonally in their color. Both players will always have a bishop of the same that can only move diagonally in one color. And then the king can only move one at a time in any direction. The queen, oh, sorry, this is the queen. This is the king. Yes. And the king can move in any direction it wants. And it can also, I don't want to confuse you, but if these two fellows here are not there, the king can move twice, can move here and here to be castle, what is called castle. But again, I don't want to confuse you. The queen, she can do whatever she wants because she's the queen. And that's just and that's just the rules. There are very cool variations of chess out there, but I don't want to confuse anyone, so I just mentioned that they exist. Captures, promotions, and castling. Whenever you take over a piece, you land where that piece is at from your opponent. So the reason this is very important is because if I train a model to always be a perfect chess machine, then it needs to know what is a legal move and what is not. If immediately it tries to move with this one to here, but there's no opponent there, then that's an illegal move. If it tries to jump over this one's here, that is an illegal move. And I do not want my model, my LLM, to do those things. So now that we're about to see the training set, before we do a run, we're gonna see how do we set it up to start training. Okay, so here it is, exactly that. There are many ways of annotating data for fine-tuning. And this particular method, or several methods here, involve, or they are part of something called supervised fine-tuning. Have anyone here heard of supervised learning before? Okay, most people? Okay, cool. So when you have supervised learning, you have the labels of something that you want. And then you have the data that leads to that. When you have annotation for chess, you kind of have the exact same thing. So this is called foresight something notation. I always forget the E because I cannot pronounce it. So you have all of the players at the back, all of the pawns, the moves that they can do, and then the opponent is in uppercase, and then the last move. So what this means is that one line stores the whole board state. This is what the model will see, and then we will give it as an input, or sorry, as a predicted output, the desired move, like a really good move to make from here, which is bishop over here, because if that knight moves and so on, and I get my queen where this one is, then the king is checked. But I mean, there's many other plays that can happen in between those. But what I want you to keep in mind or to take into consideration is that this entire thing is a string, and that is going to use that to predict the next best move based on the state of the board. So that is going to be part of our data set, and we're going to need many, many more plays than that to fine tune it to be really, really good at chess. There's another one that is called EuroSciPy. And this one goes from square to square, and there's no context needed. So it's a little bit tricky because it always tells you what is being played, but it doesn't give you the state of the board. So you can give a model, this was the last move that was played from somebody else, from the opponent, and you can kind of like give it the best move that it should make based on that. But it doesn't have a concept of what else has been played or what else has been removed from the board. So it is nice for kind of like a computer that needs to know just what's next and what has happened. If you're working in an application, that will be a really good notation to have. Then there's also standard algebraic notation. This one is kind of like for the people. Capital B is a bishop from the capital letters is going to be the white one, and the lowercase letters is going to be the blacks. So it means some bishop to b5. There's a little bit of information missed over there, but that's what has happened. And then PGN is the whole game history. So can you see what a problem might be right now? can anybody kind of like intuit in some way, like what might be an issue of any of these four? And I'll go back. Oops. Say that again. Correct. That's exactly right. So if we use this one, is really good because I can tell the model at every time what is on the board at that point in time, but it has no concept of what came before, but it is the best one to kind of like tell it what is next. Now, if we use this one, which has the whole game played, it can kind of, especially to smaller models, a game that takes forever and that really goes very, very long, and there's just a lot of unnecessary moves, perhaps with very average players like me, then it might just be useless for the model, and it kind of like doesn't know, it doesn't teach him much. It just tells him, but it's also a good signal because it gives it information about what a bad game and a really good game might be. So in a nutshell, it's exactly what you said. The state of the game versus a really good signal to what should be played next, but no information about what has been played before. A lot of information about what has played before and what could be played next, but overwhelming, perhaps, to learn. So there's one more thing that I should mention. A lot of the game, so this is a solved problem, by the way. A lot of game engines, they use something called Stockfish. It's a lot of plays and a lot of games already saved in a database. So you can immediately just use that in some ways, but you don't have any intelligence behind that. It's literally a machine playing against you. Python uses that, and it allows you to validate legality of a play. And then Stockfish kind of like says like, yep, this is valuable. This is a valid move. A valid move. You can continue. Okay, so I mentioned that I have made a little app that I wanted all of us to jump in, but it is not going to let me like I can share the URL, but it is not going to let me do it. If you want to join this, you can do it. Ooh, there's two Ramon. Oh, because I joined in the presenter mode. So whenever anybody joins here, I was going to be able to see it here, but in the repo, you're going to have something called just file. And I'm going to show you something. Have anyone here ever heard of something called make files? Okay, make files. Okay, excellent. Just file is just that. It's kind of like a make file, but it has a few niceties in it, and it makes it a little bit easier to pass variables and flags to your commands. So there's a couple of things here that I want to walk you through, because whenever you get set up with the workshop, there are two things that you can do to do it relatively quickly. So I'm going to show you just files. So, oh, that is not what I want. Okay, so this is the command runner that I'm using. If you install it, there is one command to install it. It should be somewhere here. Oh yeah, packages. You can install it with your package manager, Conda, Brew, UB, anything. It just works with anything. And after you install it, so you can do. Everyone heard of UB here? Okay, cool. So you can use UV to install, and once you have it installed, you're gonna have a bunch of commands to set up this workshop. The main command that you can run here is just install, and that's going to try to install absolutely everything. If you are curious as to what this is doing, you also have different flags that you can pass. So the all flag is going to install the web app that you just saw, the API or the backend, the deck that you just saw here, the notebook that we're going to run through with the code, and then the TUI that you can use to play chess in your terminal or in your phone if you have an Android. Actually, you can use it in iPhone as well. But yeah, so you have a bunch of targets for the installation. Then the next thing that you might want to do is there are two styles for the deck. One of the deck, the chalk style, is the one that I'm using. But if you don't put anything, it's going to use a nice white template. Then there is start. Start is going to start the back end and the front end for the web app. And then there's also Gemma is going to download the Gemma model that we are going to use to fine tune. This one is pointing to the one I have downloaded locally, so that I didn't have to re-download it at any given point. But Just Start Gemma will download it if you don't have it in your laptop. If you do have a model that you want to use, you can swap this thing here and point it towards where that model is at in your laptop, and it will use it to start it in lieu of Gemma. And you can also run the examples that we're going to be walking through. So those are the most important commands: install, start, and you're off to the races. There is a start NB as well for the notebook after you install it. So you can run, okay, let me actually go back here. So you can run just start --NB, and that is going to install the notebook. And then you also have a download models that you can use. There's also the music model that we can run on device. It's relatively small, so I think it fits in most laptops. There is the chess training code for you to fine tune it. If you want to, it also downloads the data and selects a specific fraction of it. And then session notebook. So this will open up the notebook as well. So you can do just session notebook, and then it will start the notebook. It already has the location of that notebook, and it will start it for you with UV if it is installed in your laptop. So you can test the TUI, and then there's a bunch of other stuff in here. But I just wanted to sort of walk you through them if you want to walk with me through the notebook as I go through it. Yeah. I'm going to be completely honest with you. I found that I had to do a lot of maneuvering to pass in variables with Make. And I just saw it, and honestly, I just wanted to try a new tool. So do I find it better? I find it a slightly more ergonomic than Make, but that's just, to be honest, personal preference or perception of it. It's still, LLMs can write way better Make than they can do just file, and they're really good at just files too. So if you're coding as well with assisted with AI, like, I think you'd like it. Give it a try. Yeah. Okay. So in the organization of the repo, let me walk you through it very quickly. By the way, if you have not captured the URL, you can see it here, Ramon PZG FT shop. So you can go, it's Ramon PZG FT shop. That will take you to the repo with the code for this workshop. And all of the instructions that I just walked through are going to be here as well. How to start the notebook, how to install anything, all of the commands that you can use. And then if you have APIs from different providers and you want to use them, they're also going to be here. How to start the model, how to pass in a specific model if you have one available, if you have ever used Hugging Face and downloaded something to your device, or if you have used Ollama. Anybody here has heard of Ollama? Okay, cool. So if you have used it, you have models in your device already, and you can point them to them, and then use them immediately. There's also a bunch of other stuff here, but I won't walk you through it right now. So you have the deck, all of the stuff is in there, and all of the slides are split into 5 sections. The notebooks are in the notebooks directory, and the main DB is the one that we're using. All of the other ones, honestly, don't even pay attention to them. That's dead code that I didn't have time to get rid of. And then the training commands are here for fine tuning. There's some notes there for if you want to see how I work with AI. You will be able to see in comms how do I structure a prompt whenever I'm developing with AI. You might find that really useful. You might not. It's personal preference, and yeah, you might find it useful. So, okay. So back in here, we were in slide 29. If we were able to join the room, then this would appear with your name, my name, and anybody's name in it. There's here's the technical reference, or now the mechanics of fine tuning, not like super deep level, but at a conceptual level to be able to explain how this works in the background. So transformers are the main architecture of deep learning architecture being used today for generative AI models. And the transformers is very good, but it has its own limitations. So there are variations of it as well. There are mixed hybrid models as well that combine the architecture of the transformer with something else called Mamba. Then there are other kinds of architectures as well, and different kinds of attention mechanisms. Attention mechanisms is the thing that allows you, or the component of the architecture that allows you to pay attention to what has happened and what is being generated. So, so tokens go in, they pass through a stack of identical blocks, and the head predicts the next token. So the thing at the very end. So you have the tokens, you have the embeddings, you have blocks, and the attention layer, plus the multi-layer perceptron, block N, and then you have the output head. So that the next, and then that predicts the next token. So every arrow is sort of like a matrix of learned weights. Training changes matrices, and then the 3 methods that follow, they differ only on which ones. So we can do something called full fine-tuning. Full fine-tuning, we take all of the layers of the models, and with our own examples, we tweak them to adapt them, to make them much better at the specific use case that we want to do. Now, there's something very, very, very important to keep in mind, and I didn't put it in the slide. So if this comes up, I just want you to be aware of it. When you create a base model, you have a model that only predicts the next token. It only knows how to predict the next token. It has seen a bunch of data, and it knows what data comes next. Then you have another method or another type of training, which is called supervised fine-tuning. And in supervised fine-tuning, what you are trying to do is to give base skills to the models today. It used to be that supervised fine-tuning was kind of like the thing. And then we did another similar one to do that thing again. But today, there's the next step, and that is reinforcement learning with either human feedback or AI feedback, RLHF, and then there's a couple of others. So the difference here is that once you have your base model, you might want to create a fine-tuned model that knows how to use tools. It knows how to do web search. It knows how to use grep. It knows how to use all sorts of tools that it might use in the terminals, that it might use in the environment in which it operates. You definitely want it to be able to follow instructions. And now that kind of like becomes the base model of the agents, of the next level of really big and powerful models. And then the next stage is reinforcement learning with whatever feedback we might be using. Today, they are using feedback from harnesses, from environments, not necessarily harnesses, but from environments. And these environments kind of like, it's almost like, yeah, like keeping them kind of like contained in a specific space where they have access to specific tools, they have access to specific things. Anyways, when we fine tune, we might take all of the layers of a model because we wanted to be very, very good at our use case. There's many ways in which we can do it. But full fine tuning is expensive because we update the entire model. We might be updating one that already knows how to do instruction following. It knows how to take a request from us and then do what we're asking. It might know how to use tools already, but we're fine-tuning the whole thing. And that thing can be expensive. LoRa, which is probably something that some of you have heard thrown out there. Have anyone heard the word LoRa or the term LoRa before? Okay. So LoRa stands for Low Rank Adaptation Matrix. And the key word in that acronym is adaptation. What that means is that we take LoRa adapter, we make a LoRa adapter, two small matrices. So what we make is like, what we do is that we take the base weights, they never change. We literally leave the model like that. And then we add two small matrices at the end before it makes the prediction. And what we hope is that with the fine-tune, with those two matrices being fine-tuned to our use case, we nudge the model in that direction. It is much, much cheaper to train a LoRa adapter and attach it to your base model or to your fine-tuned model than to fine-tune the whole thing. I mean, you can do an adapter in relatively, well, depending on the size of the model, you can do it relatively cheaply in comparison to fine-tune a very specific model. So everything else stays frozen. You attach a new little piece that you have fine-tuned for your specific use case. And then you also have QLoRa. So QLoRa is sort of like the same detour, but the frozen base is a quantized model. So remember that quantization is, we have a model whose weights are 0 point and then 16 decimal places. And then with a quantized version, we have a much smaller footprint or not that many decimal places. Again, that's a bit of a hand-wavy explanation, but that genuinely is kind of how we reduce the footprint and the size of a model. And then what we do is that we train an adapter on the quantized version of the model. Usually quantized versions, the lower you quantize, the more you quantize, the dumber the model becomes. I don't even want to use that word, but the less capable the model becomes. So that's also something to keep in mind. A lot of times is indistinct for what you might need to use the model for. That loss in capabilities is marginal. You might not even notice it. So those are kind of like the three ways of looking at it. You can do a full fine tune of everything. You can have an adapter on the fully trained fine-tuned model already, or you can have an adapter on the base model. And you can have an adapter on the quantized version of the model, which is usually already fine-tuned to follow instructions, to use tools, and so on. Okay, so what do the recipes look like? So for us, at least in the notebook, we have position and move. What is the state of the board? Where do we want that what do we want that next move to be? We have images and we have captions with specific styles, with whatever we might want to do. Then we have audio, where we have music gen, and I'm going to show you an example of how you can, actually, I changed it earlier today. We have something called Wave to Beck, and I'm going to show you how to fine tune a model to recognize different genres of songs. And then in the last one, we have videos where we have different scenes, and then we want an adapter for a video generation model, so that at the end it generates videos in the style that we want to use. So this is something that I worked at the beginning of the year. Music, I worked on music classification and music generation 2 years ago, and retrieval as well. That was my first time ever touching music. I worked in videos early this year, and it is amazing when you get to see a little bit under the hood, like how this blob of numbers makes just unbelievable stuff. Okay, so what does this look like? So one move and then kind of like 6 rows. So you have a prefix. Where did the model come from? These are kind of like the styles that you could put your data in. So we're going to have a Python dictionary or a JSON line, a JSON-L with the data, the key value pairs that we need. One of them might be input to the model. Another one might be expected output. Another one might be instruction. Input might be additional information to the model, and then the output is what we want. So here we don't have any prefix because the model nothing has started. It is the very first move. Here we have the FEN notation, the forced something something notation, and we have the state of the board, and then the target move, and again JSON, pure JSON file. So we're going to have thousands of lines or hundreds of lines of what valid and really good moves are based on the state of the board. Then we can also have FEN plus the legal moves. So we can have, so this is what I mentioned, like you might have a request from the model. Hey, this is the state of the board. And your task in the system prompt or as the main instruction is figure out the best move based on the state of the board. And then you can also pass in as input. Imagine if we were making a paper, doing a summary of something with ChatGPT or another model. You give it a bunch of documents that you wanted to synthesize for you, and then you want to figure out the last piece once it gives you a good summary of all of those models. So here we're telling it, hey, these are the only legal moves that you could do right now. So then the model will pick based on that. And then the board tensors. So this has to be represented as a numerical. It has to be represented numerically. So you might also be able to. Sorry, let me backtrack. You can represent the tokens in a numeric way, but you can also represent the board in a numeric way. So you see here that it says 8 by 8, which that's the board, move class, and then UCI compliant, which is, it is a legal move. And then this is the next move. This is what you're targeting. This will be the target of it. Then you can also pass it the policy target. So I'm gonna show you what a policy is in a second. If you have a harness like Cloud Code, like Codex, like any of these coding agents that you can have a model on top and then it can code for you. It has a lot of things that it can do and it cannot do. And when it does something right and something correctly, then it's going to get 1 point. And then if it doesn't, it's going to get minus a point if it does something incorrectly or if it tries to do something that it wasn't told to do. And then the RL trajectory will be, we have the state of the board, we have the action that it could take, we have the reward for taking that action. If it doesn't take it, then we subtract it. And then we have the next state. We can do that as well. So we can, now what I want you to capture with this is that the data is the most important thing. And how we set the data up is going to set us up for success or is going to set us up for failure. So is the game over or not? We can also tell it. And that way it kind of like understands that the best move that it's picking is not necessarily to finish a game or in a game that is completely lost, but it's in a game that is still going. Okay, so in Python chess, you can think about that tool in a way as you don't put a model inside of Python chess, but the tools that it gives you, if you give them to a model in a similar tool to a harness, to a coding agent, then you also have a little chess harness. And that chess harness, when it makes an illegal move, you will put in a -1. And you say like, no, this wasn't good. And he knows that he cannot make that move again. But if it makes a legal move, it's kind of like, okay, well, that was good. But now it's at 0. It has no value. That game or that round of training has 0 value. And it's kind of like, it made a check. And it's kind of like, oh, this is a really, really good move. So I need to keep going. Whoa, I did checkmate. So that is a 10. So that game was really good. And it finished quickly. So if it starts learning that the faster it does checkmate, then the faster it will get its reward, then it will start trying to hack its way around it. And that is one of the reasons why we always want to give, or sometimes we kind of want to give it the legal moves as well as input when the model is about to do, is about to make another move. Last piece. I know that there's a lot of information here, but even though the data for training has to be formatted in JSON or in a specific way that we can use, that is not how we get back the information. Usually we use a prompt template. And during the second piece of fine-tuning, a model might have been fine-tuned to follow instructions with a very specific template. And if we don't use that when we're decoding the output, then we're going to get gibberish. We're going to get tokens that make absolutely no sense whatsoever. So here you can see the prompt template. You are a chess engine assistant. Position is FEN. And then here you have the position. So we have the data comes in JSON, we format it using the prompt template, and then we pass it to the model. So legal moves, here are the legal moves that you can use. They don't necessarily need to be provided to the model. They can be provided. And it says, return exactly one move from the legal move list. Respond with JSON, move, UCI, a compliant move. So then, recently, this past in the last 2 years, I have been doing quite a bit of coding, low leveling, in low level programming languages. And the more I do it, the more I love Python. The more when I come to Python, I kind of feel like a lot of libraries out there, they're giving you a config file. They're giving you key value pairs for in lieu of coding. And I am not suggesting I want to, by any means. I appreciate it because it makes you go really, really fast. But a lot of times, the ease of use for making something happen doesn't let you pick under the hood. And this is why I wanted to give you kind of like a lot of details before I got to the coding, because I felt like that would be more useful than 5 lines of code. Here's your fine-tuned model that you can go and look at the documentation. Now, Transformers is really, really good at this. And you do have very, very small lines of code to get a trainer up and running. So in the transformer here, you have the auto processor, and you can bring Gemma. You can apply the template, and then you kind of like have the render, like the processor, completely set up to do a training round. That is with the Transformers library. And again, we're going to go to the code now. Whenever you get the prompt template back from the model, it literally looks like this. Beginning of sentence, we have a special token to let the model know that this is where it starts, the conversation. And then we also have a special token to let it know that this is the turn of the other person, or that this is the turn of the model, that it has ended. So the turn, model, special tokens, move to this way. Because it is in JSON, if it doesn't get it wrong, then every time it comes to us, we can immediately apply it to the UI, and then take that JSON file as a little piece of data, and then move the model, the piece to where it's supposed to go. So it will be kind of like this. You have a base and an adapted model, one frozen suite. So you have legal moves. They come in as JSON. So you have the input here, the JSON. So you have the base, and then you have the adapted model. So the base might still give you, so the reason I added this is because you're going to get a lot of this malformed JSON or malformed data. And a lot of times, before the newer LLMs that we have today and the newer models that we have today, you will have to do a lot of maneuvering in plain Python code and with regular expressions to be able to like detect that malformed data. Nowadays, an adapted model, the more examples you give it with well-formed instructions, then the better they become at giving you exactly what you need. They're not perfect, but the better they become at giving you what you need. On Sloth, they are very good at coming up with fine-tuned versions of all models that come out. So you have, they have a class called fast model, and then they have a little config that you can use with it. And they already have all of the fine-tuned versions in their repository in Hugging Face. So you can use those, or you can use the straight up ones from the providers like Google here. You can load them in specific quantization methods, which is really, really good. They have others for different levels, Q6, quantization at 6-bit precision, 8-bit precision, 2-bit precision, and so on. And then you get the model that you're gonna be training. We're gonna go to the code in just a second. We're almost done. There is one more fine-tuning provider. There's plenty, by the way. There's plenty. And this one's called Axolotl. And you literally have one config file, and it is a CLI, and it starts the training run for you. Very, very easy to use, and you just need, but it's not code in itself. It's kind of like a CLI and then a config file. It's an option. You can also code it by more or less, not necessarily by hand, but you can code a little bit more with JAX. I have an example in the docs or in the notebook with JAX, and you can code a little bit more of the process of creating a LoRa adapter with it. Okay, so you can start very straightforward with a UI. OnSloth has a really nice UI that you can use for fine tuning. Actually, so I want to show you what you can do with OnSloth. You have a train spot here, and you can find a lot of recipes. So you can search for a data set in Hugging Face. So I could put here chess, and it's going to find a bunch of chess data sets that you can use. You can find a data set locally as well, or if you have it in an Amazon S3 bucket, you can take a subset of the data set. You can select a random sample. You can split it between train test split, select the ratio. You can create an evaluation split as well, so a third one. You can tweak the parameters here. If you're going to make a LoRa adapter, you also have further settings for the LoRa adapter, and there's a new version of OnSloth. And then you also have the training pipeline. So notice here that I can pick the models from models that I have already downloaded locally. So you can see the Music Gen Small there. You can see the Gemma 4 E2B. So QAT stands for Quantization Aware Train. So the model knows that is, or this is my understanding of it, that the model knows that is being the size of it is being reduced. And then you can have the specific model. So you can use a local one, or you can use the Hugging Face model. You can say which type of quantization do you want, which type of adapter do you want to create? The one based on the quantized version, or one based on a full 16-bit precision model. You can do a full fine tune as well and continue pre-training. So my this laptop has an 8 GB VRAM. I can train, and I have trained in my laptop the Gemma 4 2B model, fine-tuned it to play chess, and it's the one that I recorded the video with, and it did pretty well. If you have a specific model that you have to sign up for, or you have a private model, you can also input your Hugging Face key. And honestly, this is the level of abstraction that we are at today. You can fine-tune completely from select the model, select an available data set, select the type of thing that you want to do, and then just let it run. It will download the model and it will leave it on your local file in your cache, and you can access it from there. If you remember from earlier, my command with just for the model, you're going to have it in your cache, in your Hugging Face hub models, and then it's going to be in one of those files there. So you can fine tune it on your device, and then off you go. You can use an API. I mentioned thinking machines with the video of the corporate speak being reduced to nothing. And then we have the config with Axolotl, which is a one-line command line tool utility to train. You can do OnSloth and code about 5 lines, and then you can use raw JAX and then read the model in. And spend a lot of time like trying to figure out how to do it. JAX also has an implementation of Gemma, but you can also do that. That's kind of like the layer of abstraction of all of this. And then for image, you have the images, you have the caption. For audio, you have the audio, you have the caption. Video, you have the same, a clip, but you might recall that I mentioned text to video, image to video, keyframes to video, and video to video for style transfer. There's one more thing. You can train for, so I have played around with this, but the payout can be very hit and miss. You can make an unbelievable model, or you can make a completely ridiculous model that doesn't know anything. So what does this mean? Model merging means I fine-tune a model of Gemma to be really, really good at chess. And then I fine-tune another model on the same Gemma to be really, really, really good at coming up with real world use cases based on the log of a game. And now I take the average of the weights of both models. That's one method of merging models. And then I get a mixture of the two. And that can be really, really good, or it can be absolutely awful. There's different methods as well. One is called Franken merging, I think it is. And it is what you think. You kind of like take one layer from one model, one layer from the other, and you kind of like stack them all together until you have the same amount of layers from the initial model. And then you can mix models that are completely different from different places, like a Gemma with a Quen model and so on. So there's lots of ways of merging, and it is interesting. I think it's underexplored, but perhaps because state-of-the-art models have gotten so good that this has become maybe a little bit irrelevant. But yeah, take it home, use what you may here. It's a lot of